Okay, so today I want to go over the graphs of sine and cosine functions. So this is me, and I will be writing solutions as best I can so that you can look at this video later if you need to look at it for some help. This link to Khan Academy explanation of how we get a trig function graph, especially sine and cosine, from our idea of a unit circle is really highly recommended. So if you haven't looked at that video yet, you might go look at that and then come back and fill in this. The other thing that you should have is the textbook open. Okay, so let's talk about the graph of sine of x. So if we draw an axis, and you're just freehanding like I am, it's okay if it's just a rough sketch. We do want to label the x-axis and the y-axis, so I'll put some marks here and then I'll start to describe them. Okay, so if we think about the unit circle, I'll draw it over here as best I can, something like that. What we'd been talking about before are angles, so we had opened up an angle theta, say to here, and then where it hit the unit circle was cosine theta, sine theta. So for an input here, sine of that input was the height. If I open up that many, let's say radians, and I plot the height on the unit circle as I hit out here, that's what sine is. So just thinking of that definition, let's plot a few points that are easy to identify. If now I think of an input, let's just call it x, and a height y, okay? As I plot an input of, let's say, pi over 2 radians, how high is that? Here we go over to pi over 2, and we hit the unit circle here. The x-coordinate is 0, the y-coordinate is 1. So sine of pi over 2 is 1. Another easy angle to see is you look on a unit circle, go all the way out here. We hit the unit circle at -1, 0. So what is sine of pi? It's 0. And we do 3 pi over 2. So we open up here, and we think of the x and the y. The y is the sine, it's -1. And at 2 pi, we've gone a full rotation around the circle. Here we go. And we look at the height as we hit the unit circle right here. And we're at the 0.10. So sine of 2 pi is 0. But of course, that's also the sine of 0, because sine is periodic. It repeats. Let's see what happens as I go negative. So these would be positive inputs. These are negative inputs, and negative inputs mean, on the circle, that means I go back the other direction, so this way. If I go negative pi over 2, that's here as a negative input. What's the height as I hit the unit circle? That's -1. Okay, and I could go negative pi. Sorry, pi negative. That means that I've gone over here, my unit circle, go negative pi, I hit here, and what's the height? The height is 0. All right, and at this point, we're going to sort of say that the sine function, as I go around the circle, and it's changing in a nice, smooth way that produces a drawing that is nice and smooth over here, connects the dots that we have already filled in. And you see this nice, smooth up, down, and it repeats. It goes on this direction, goes on this direction, but I've captured several of the values here. So where are the x-intercepts and where are the y-intercepts? Well, you can't have two y-intercepts if you're a function, and this is a function. We have one y-intercept right here. Okay. That's also an x-intercept, because an x-intercept is where do you hit the x-axis? Y-intercept, y-axis, right? I've hit right here. My x-intercept is where I hit the x-axis. Also here, 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 here. In fact, there's a pattern to all these places we're hitting the x-axis. So sine of x is 0. Our height is 0. We're hitting the x-axis everywhere that x is a multiple of pi. So we see that. And we have a y-intercept right here at the origin because the sine of 0 is 0. Okay, so that's a graph of sine of x. It's taking what's happening with the unit circle and then plotting it one input at a time. What's the corresponding height? And since the sine function is periodic, this will repeat and go on and on and on. We can also say what the domain and range are then, because if this repeats on and on and on, it's defined for all inputs, then the domain is all real numbers. One way of writing that is negative infinity to infinity. The range are what are the possible outputs? What are the possible y values? So as you look at this graph here of sine of x, what are the possible y values? Well, we see we go as low as -1, and we actually hit it repeatedly. We go as high as 1, we actually hit it repeatedly. So my range is all possible numbers in between, -1 and 1, and I want to include them, so I draw them with those square brackets, not the open parentheses. Okay, so the graph of cosine of x is very similar, and I'll just hit the highlights then. So I like to think about the radians as inputs. So you see here that I have my unit circle radians. And let's include a little bit of the negative side. And cosine on a unit circle, of course what we have is a very similar idea. We open up so many radians, say theta, and what we're looking at of cosine of theta is what's the x-coordinate as I hit this unit circle. Well, my x-coordinates are always between -1 and 1, and that's of course what I'll see here then as I plot y equals cosine of x. I will see outcomes that are always between 1 and -1. And there are a couple of key points that are easy to see. So cosine of 0, for example, what's the x-coordinate as my input is 0 radians? It's 1. So up here. Okay, so that does not have the same y-intercept. What's cosine of pi over 2? So we open up here. What's the x-coordinate? 0. What is it at pi? -1. Here we go to 3 pi, back to 0. And 2 pi, of course I'm back where I was at 0, right here. If you go the other direction, go back. Cosine, the x-coordinate here is 0 at -pi over 2. Go back even more. There we go. And we're going to connect them in a nice smooth fashion. Something like that. Okay, good. That's a pretty good approximation. And we see then some similarities with the sine curve. We see that same nice smooth oscillation back and forth, back and forth. We see that our domain and range are the same, so you should draw for domain and range, you should repeat the same answers as you did for sine. But we do have a different y-intercept. Here's the y-intercept here at 1. And we have different x-intercepts, so where we're hitting the x-axis will not be at the whole integer multiples of pi, but at the odd integers of pi over 2. So k has to be odd. You see that? Because it's 1 pi over 2, 3 pi over 2. The next time will be 5 pi over 2. Odd integers also can include the negatives, so we have -1. So negative odd number times pi over 2, and we have an x-intercept. So there's a different form for the intercepts there. But otherwise, it really looks similar to our graph for sine. And you should plot these in your calculator to get a feel for how they graph. If you do, then make sure you're setting your window appropriately. You want your y values to be between -1 and 1. You might look at an x window between, I don't know, maybe -pi over 2 to 2 pi. That might be pretty good. So between here and here. And you want to make sure that your calculator input is in radians. And then you can tell it what size step you would like to see plotted. So you could choose pi over 2 for the step size. That makes a nice smooth graph that looks a lot like what you drew. Okay, so let me go to the next page. Okay, so on the next page we're reviewing a little bit about function multiplication. What effect does multiplying 3 have on the graph of a function? So basically, what does this function look like compared to this? Hopefully you remember that a times f of x, where a is a number bigger than 1, corresponds to a vertical stretch by a factor of a. So it basically, however high f of x went, 3f of x would go 3 times that height. So the range gets changed. The allowable inputs are still the same. If I can plug x in here, then that's exactly the stuff I can plug in here. But the height, the y values, which is the range, change. Whatever the y values were here that were output, they're now 3 times as much here. Okay, so what's the amplitude? Of course, if you've done your reading and hopefully followed the videos, you know that amplitude corresponds to a distance between the midline distance between, I'll abbreviate between, midline of a sine graph and, let's say, the highest point. So we look at this 5, and we know that means there's a vertical stretch of the function and that the range is changed. So now instead of being between -1 and 1, 5 sine of x is between -5 and 5. Now where the highest value occurs, where the lowest value occurs, that stays the same. The overall shape here, if I zoom out, looks the same except my range is now stretched. Amplitude is what's the distance between the midline, that is the middle of a sine graph going right down the middle, and the highest point, say here, and that distance is 5. So the amplitude will be 5. Okay. If a function has period 2, what does that mean about its graph? That means the graph repeats. And the distance, and if the period is 2, then it means the shortest distance. The distance between repeating parts is 2. So what we mean by repeats is that the same height then happens again. So if I have a function at some point a, however high that function gets as my input is a, it's going to be the same height it gets if I go 2 forward. So that's going to be true for all a in the domain if a function is periodic with period 2. What's the function sine of x? Is it repeating? Yes. Does it have a period? Yes. We can look at the graph. And what we should see is a piece that repeats completely. We want to see a full cycle. What I want to see is how far do I have to look from one point to the next so that what occurs between those 2 points could just be repeated over and over and over, and that would capture the graph. Well, if you notice, if you look at the graph of sine of x, you could, for example, look just between 0 and 2 pi. You would see all the possible shape of sine, and then what happens after 2 pi is just a repeat of that. Okay, so the period is what's the distance between repeating parts. It's easy to see that the distance between repeating parts then is 2 pi. Okay, with your graphing calculators, you're going to plug into one line. This could be maybe y1, and this one could be y2. What I hope you noticed is that the functions actually overlap. because go back and look at the front page of what you drew for sine of x and cosine of x. They're actually the same graph, but with merely a shift. So if you take the cosine of x graph and you shift it to the right by pi over 2, you're going to get sine of x. So look at the graph and convince yourself of that. Shift it to the right, pi over 2. And you're going to get the exact same thing you get for sine of x. Well, cosine of x shifted right by pi over 2 is exactly what that means. So that's why when you went to graph them, you only saw one output, one function spit out. All right, this is captured in your textbook, so if you have any difficulty finding it, just look in your textbook for what is the amplitude. If you have a multiplier in front of a sinusoidal, so a sine of something, graph, then our amplitude is the distance, so it always has to be positive. So we take absolute value of that coefficient in front. So this could be 6, and so the amplitude would be 6. It could be negative 1/3, and the amplitude would be 1/3. So there are a lot of different options for that number in front. What's the period of the graph? So there's a formula here. If we have an omega, we would do 2 pi over omega. Again, that could be in absolute values because we want to have the positive distance. Period as a distance. So we'll do that. All right, because we know that multiplying the input changes the compression in the horizontal direction. And there's a formula for that change. All right, and then the last question is, determine the amplitude and period of this graph, and then check your answer by looking at the graph in your graphing calculator. So the amplitude is 3, the period is 2 pi over 4, or pi over 2. And what that means is that it looks like sine, okay? It looks like sine, except the amplitude is telling me now that it's stretched out, so I don't go negative 1 to 1, I go now negative 3 to 3. 3, negative 3. And the period being pi over 2, now usually when I graph sine of x, I think of the period being 2 pi, so I plot from 0 to 2 pi, and I see the whole nice, smooth cycle. But the period's pi over 2, so that tells me that everything that happens with a sine function happens between 0 and pi over 2. This should look like a complete cycle of sine. It happens between here and here. And then after that, I just see repeating portions. Okay, so maybe that wouldn't be 2 pi by the time I got out there, but I would repeat the portions and they would look the same as what I saw between 0 and pi over 2. So graph that on your calculator. You know that for sine, we kind of go up through the origin. We reach a highest point, then we come down, we reach a lowest point, and then we come up. And that's the life cycle of a sine curve. Go origin, reach a highest point, down, reach a lowest point, back to the origin. So something like that. Okay? All right, so you should see something like that on your graph. And where is it hitting then? Where's this x-intercept? Well, on the original function, sine of x, we hit the x-intercept at pi. Where do you think we're going to hit it here? So normally we hit it at pi. We're stretched out from 0 to 2 pi. So halfway through, right? Well, what's halfway through from 0 to pi over 2? It's pi over 4. Okay. Right, and then so where is this highest point occurring? Well, it must be halfway between 0 and pi over 4. So that must be at pi over 8. All right, so these are the basic shape, and then it would repeat, repeat, repeat forever. Let me finish the graph there. We keep going. I'm being really kind of loosey-goosey here with the labels, but it goes something like that. So it looks faster. So if inside here you have a number bigger than 1, what you see is a sine graph that looks like it's happening, but at a faster speed than regular sine. And if you see a number out here that's bigger than 1, it also looks stretched up and down. Okay, that's enough for now. Hopefully this was helpful to you, and I'll see you in class Wednesday.